On the night of August 15, 1977, a radio telescope in Ohio was scanning the sky for any stray transmissions. What the computers printed out was an incredibly loud, razor-thin spike in radio waves. It was precisely tuned to the frequency of neutral hydrogen, a channel astronomers long suspected an intelligent civilization might use to communicate. The data sequence was so striking that the astronomer reviewing the printout circled it in red ink and wrote a single word: wow. For decades, scientists pointed instruments back at that exact spot in the constellation Sagittarius. They listened for hours, then days, then years, but the sky remained completely silent. The signal never returned. Fast forward 40-odd years to our closest neighboring star, Proxima Centauri. In 2020, telescopes picked up a new transmission coming directly from that system. They called it BLC-1. Like the WOW signal, BLC-1 was a concentrated, narrow-band frequency. It even drifted slightly, mimicking the exact Doppler shift you would expect from a physical transmitter located on a rotating, orbiting alien planet. Yet, despite thousands of hours of follow-up observations, BLC-1 disappeared into the void and evaded every attempt to detect it again. For nearly 50 years, radio astronomy has been haunted by these isolated flashes in the pan. We are finding out that the universe is remarkably adept at generating noise that looks exactly like artificial technology. In 2025, researchers finally got a grip on what caused the 1977 anomaly. They ran a massive computational archaeology project, digitizing over 75,000 pages of archival data from the original observatory. Their analysis points to an extreme, natural astrophysical event called magnetar-triggered hydrogen superradiance. To understand this process, picture a magnetar, a highly magnetic, ultra-dense dead star. Occasionally, these remnants violently expel an intense burst of high-energy X-rays. If that flash collides with a freezing interstellar cloud of neutral hydrogen gas, it rapidly energizes the atoms inside. The entire cloud becomes momentarily inverted, meaning the atoms synchronize and dump all their newly acquired energy at once. The result is a highly concentrated laser of radio waves, fired off in one specific direction. On that night in 1977, the Earth happened to drift perfectly into the path of one of these brief cosmic lasers. The telescope recorded the beam for exactly 72 seconds, before the planet's rotation carried us out of alignment. The transmission didn't contain an alien greeting. We just happened to hold the winning ticket to a one-off astrophysical lottery. So what about the BLC-1 signal from Proxima Centauri? Exhaustive data sifting revealed that it originated much closer to home. It was human-made radio frequency interference, likely a piece of earthbound electronics that drifted in frequency, and perfectly mimicked what we thought an alien beacon would look like. Beyond our own stray electronics, we also have to contend with stellar space weather. Most stars in our galaxy are volatile red dwarfs, and their planetary systems are constantly battered by thick, turbulent plasma. Imagine an intelligent civilization actually manages to broadcast a clean, razor-thin radio wave out into the cosmos. As that broadcast passes through the erupting stellar winds of its home star, the plasma physically distorts the wave, smearing it out across a wide band of frequencies. This scattering effect practically deletes the precise signatures we search for. Meanwhile, chaotic events like wandering black holes tearing apart stray stars produce rapidly evolving radio flares that look entirely unnatural to our sensors. Between our own terrestrial interference, plasma scattering, and exotic star collisions, the cosmos is actively flooding our receivers with imposters. Separating a genuine technosignature from petabytes of cosmic static exceeds human capacity. Processing this volume of information requires a system that can make decisions as fast as the data arrives. Researchers have now integrated an advanced AI architecture called the Holoscan platform directly into the Allen Telescope Array in California. This system ingests and analyzes enormous streams of astronomical data 600 times faster than previous algorithms, operating well over 100 times faster than real time. It actively cross-references incoming radio waves, recognizing the complex patterns of natural cosmic static and automatically filtering out false positives and human interference like BLC-1. We are no longer waiting for an astronomer to notice an anomaly on a paper printout days after the fact. The software handles the noise, clearing the path for the real thing. So if the famous anomalies of the past century were just tricks of physics or local interference, what should we actually be looking for? In 2024, an experiment called A Sign in Space beamed a simulated alien message from an orbiter around Mars back to Earth. A father-daughter team of civilian cryptographers managed to decode it. The decoded message contained a sophisticated visual payload, three-dimensional molecular diagrams of amino acids, reconstructed through cellular automata algorithms. Cataloging these extreme natural phenomena doesn't shrink the search, it focuses it. By using AI to clear the board of imposters, we have transitioned from hoping for a lucky catch to a systematic, data-driven hunt.